Hello, my name is Sam Ficarelli, and today I'm going to be talking about my Capstone project. The purpose of my project was to work with Arduino and utilize it in order to create a small rover that would be able to avoid obstacles. Now, Arduino is an electronics prototyping platform which was designed to make electronics projects cheaper and more accessible to a wider audience. Now, there are two sides to the Arduino platform: hardware and software. The hardware aspect of it involves using a microcontroller board to connect to input and output devices. Meanwhile, the software side of it involves using the Arduino software environment to create a program, also known as a sketch, which will essentially allow you to configure the hardware devices and allow them to communicate with one another. Both the hardware and software are open source. The Arduino software environment is free to download, while the hardware reference designs for the microcontroller boards are available under an open source license. Meaning, if you so desired, you could build your own Arduino board yourself, or even legally design your own, manufacture it, and sell it to others. Now I'll be talking about some of the main components of an Arduino microcontroller board. On each board, there's a microprocessor, a small amount of flash memory, input-output pins, a USB port, and a DC power jack. The microprocessor is where the board takes digital data as an input, processes it according to stored instructions, and then provides results as an output. The flash memory is where the actual Arduino program is kept, which acts as the set of stored instructions for the microprocessor. The input-output pins are used to connect the Arduino board to external devices and allow them to communicate with one another. The USB port or DC power jack are used to connect the microcontroller board to an external power source. The USB port also allows the Arduino board to communicate with a computer and allows you to upload a program to the flash memory from the Arduino software environment. Now, as I mentioned before, there are two types of devices you can connect to the Arduino board: input or output. An input device would be anything that sends a signal or reading to the microcontroller. An example of this would be a button or some sort of sensor. An output device would be something that receives a signal or command from the microcontroller, such as turning on an LED light or turning a servo. For the rover I've put together, the range sensor would be considered an input device, and the motors would be output devices. Here is a front side view of the rover. As you can see, a range sensor is mounted on the front, and two motors are located on either side. Each motor is attached to a cog, which are placed in a track. As the motors spin, the cogs pull the tracks forward, propelling the rover. On each of the motors there is a positive and negative lead. By running a current through these leads, the motors will spin. Likewise, if you run the current in the opposite direction, the motors will also spin backwards. How the range sensor works is, it sends out an infrared signal, then records the time it takes for the signal to return. It then sends that time reading to the Arduino board, which can be utilized in a program, such as the one I have written for this rover. Also, even though you can't see them in this picture, there are two battery packs located on the underside of this rover. One is a 9-volt battery used to power the Arduino board, and the other is a 4.8-volt battery pack used to power the range sensor and motors. Here you can see a top-down view of the rover and get a better idea of how the hardware is connected. Firstly, on the back side of the rover, you can see a red and black wire. These are connected to the 4.8-volt battery pack. The black wire represents the ground, and the red wire is the 4.8 volts. These two wires are connected to two separate lines on a breadboard. A breadboard is used as a prototyping device for electronics and allows you to complete circuits without the need of having to solder wires or pins together so that a current may pass through them. Both the 4.8 volts and ground are connected to the pins on the motor controller chipset, which I'll talk about in a bit, and then also to the range sensor. Also note that the ground pin on the Arduino board is connected to the ground of the 4.8 volt battery pack using this brown wire. Here, you can once again see that the ground and 4.8 volts are connected to the wires of the range sensor, giving it power. You can also see that there is a yellow wire that connects the range sensor to the fourth analog input pin on the Arduino board. This is the line that the range sensor will use to send the distance readings to the Arduino. This is the motor controller, which as its name implies, is used to control the motors. I've made this diagram to show what each of the pins on the motor controller are used for. The 4.8 volts and ground are connected to the battery pack, and is used to power the motors. The purple line is connected to the 5-volt pin on the Arduino board and is used to power the motor controller. The green wire is connected to the serial output pin on the Arduino, which is the output pin number 1 on the Arduino Uno board. This is the line that will be used to send commands to the motors from the Arduino. The orange wire is connected to the second output pin on the Arduino and is used to reset the motor controller. The last 4 pins on the motor controller are connected to the positive and negative leads of the motors. Depending on the command you send to the motor controller, it will change the way the current flows through the motors, allowing you to move them either forward or backwards, and at different speeds. Now, I'd like to take a look at the code for the program I created to run the Rover. Here at the top, you can see that I use Software Serial, which is an Arduino library. A library is something that provides extra functionality in programs and contains a predefined set of functions and commands. The Software Serial library in particular allows for serial communication across pins 0 and 1 on the Arduino board. Underneath that, you can see that 2 variables are created, distance pin and reset motor. These are both going to be used to denote pins on the Arduino board. The distance pin variable will be used for the 4th pin on the Arduino, which I already mentioned is connected to the range sensor, and the reset motor variable will signify the 2nd pin on the Arduino, which is connected to the 5th pin on the motor controller. Now we'll look at the setup function. This is the first part of the program that the Arduino board will go through whenever it is first turned on. As you can see, the first thing that happens is that reset motor is designated as an output device. A low signal is sent across the reset motor pin, and then is switched back to high. This is essentially used to turn the motor controller off and then back on. By doing this, it will clear the previous state of the motor controller and trigger it to reinitialize. After the motor controller is reset, the serial communication will then begin across pins 0 and 1 so that commands can be sent to the motor controller. After the Arduino has run through the setup function, it will then move on to the loop function. As long as the Arduino is turned on, it will continue to go through the code that you have in here until it is turned off or is reset. In the loop function, there are 2 other functions that are going to be executed, motor forward and detect range. The motor forward function was created simply to send a command to the motor controller in order to make the motors move forward. The detect range function, however, does a number of things. First, it creates a variable called distance and gets a reading from the distance pin, which is connected to the infrared range sensor. An if statement is then created, checking the distance variable. If it happens to be within a certain range, or in other words, the rover has gotten close enough to an object, several other functions will be executed. The stop motor, motor reverse, and motor turn functions. These functions are also used to send specific commands to the motor controller, which I'll go over now. Here we're going to look at the motor forward function. Whenever sending a command to the motor controller, there are 4 bytes you must send. The starting byte, the device byte, a byte to represent the motor number and direction, and a byte representing the motor speed, each of which will be in hexadecimal. The starting byte signifies the beginning of a command, and it will always be 0x80. The next byte you send is the device byte, which identifies the device type for which the command is intended. In this case, it will always be 0x00 to denote the motor controller. The next byte determines which motor the command is meant for, and which direction it should turn in. 0 means the first motor should move forward, 1 means that the first motor should move backwards. Meanwhile, 2 means that the second motor should move forward, while 3 means the second motor should move backwards. The final byte you send to the motor controller represents the speed at which the motor should turn in. This can be anywhere from 0 to 128. As you can see in the motor forward function, there are 8 bytes sent to the motor controller, a total of 2 separate commands, both of which are meant to make motors 1 and 2 move forward. You'll notice in this code that I have the motors moving at 2 different speeds. This is because I had a problem with the right motor on the Rover, which would spin slower. To offset this, I changed the code to make the left motor move even slower than usual. So again, to summarize what this program is meant to do, it resets the motor controller, then begins the serial communication to the motor controller. It will then continually send signals to the motor controller, making the motors move forward, while receiving distance readings from the range sensor. Once the range sensor detects that the rover is getting close to an object, signals will then be sent to the motor controller telling it to stop, move in reverse, and then turn around. Once the rover has turned around, it will then once again start moving forward until it gets close to another object, where it will turn around again. Now, I'd like to give a small demonstration of the rover in action. Okay, now I'm going to plug the rover in. And remember, as soon as I plug it in, it's going to move forward until it gets close to an object, and then it'll turn around. So as you can see, it's moving forward. And as I place my hand in front of it, it'll stop, and then turn around. Again, it'll keep going forward until it gets close enough to an object, which it will again stop and turn around. Well, that's everything I have for now. If you have any questions or comments, I'd be happy to reply to them if you post them below. If you'd like to view more information about this project, I'll post a link to my blog in the description. And that's it. Thank you for watching.